All right, hello, welcome back. So I have checked the video and it turns out my audio was working. And so I thought this would actually be a really good opportunity to kind of explain a little bit more in depth what I actually did in solving today's problem because honestly, I did a horrible job at explaining what I was doing. So to do this, we need to understand the problem a little bit more first. So the problem says it gives us this representation of a ski slope or a mountain slope. But what the problem says, and then the problem that gives you an example of this kind of shorter ski slope, but it also says that there's something special about this pattern. It says the same pattern repeats to the right many times. And so what it's saying is that even though this is the input that we've gotten for this problem, this pattern actually repeats infinitely many times all the way over to the right forever, right? And so the first thing that brings to mind is this idea of, well, we can't reproduce this pattern infinitely times over to the right in order to solve this problem because a computer has limited memory. And so right in there is this little problem of optimization. How do we efficiently compute whatever the challenge needs us to do with this map when the map is of an infinite size? We need some way of storing the finite version of the map, but still operating on it as if it was infinite. And so we'll keep that in mind as we look at the question. The question is asking, basically, if we start in the top left corner, and what we do is it specifically says, if as we move down the slope by going right 3 steps and down 1 step, and we keep repeating this, right? So you can see it highlighted on this in this example. You can see it highlighted with the O's and X's. If you go 3 right, 1 down, and then from that spot you go 3 right, 1 down again, and then from that spot you go 3 right, 1 down again, and so on until you reach the bottom line. It's asking how many trees, which are represented by hashes in this example, do you encounter? And so if I do it more concretely with with the lines in my example, I'm going to need about 11 lines to make this work. So this is the example. This is my actual input, right? Not an example. So say we start in the top right, top left, and so we can count. We can keep count here. We start here. We don't hit a tree, so no tree. We go 1, 2, 3 to the right, 1 down. That is a tree. So that's a tree, and we increase our tree count. From here we go 1, 2, 3 to the right and down 1. That is a tree. So we increase our tree count again. From here we go 1, 2, 3 and down 1. That is a tree, and we increase our tree count again. Now you can see that there is a pattern here, right? If I label these rows, so in JavaScript, remember indexes start at 0. So this is column 0, column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So I'm just going to label it like this. Yeah, this gets a little bit hard to read, but it works. So you see the last column we're at index 30, but because we started counting at 0, there are actually 31 rows in here. Now this is where the interesting thing comes from. Actually, let me do it like this. Okay, so I've labeled all the rows and all the numbers. Now what you can see about this is we can programmatically, and this is what we exploit. This is what I exploit in order to compute this with one formula. You can see that the column that we're checking is related to the row that we're on, right? On the first row, we're on row 0. The column we're on is column 0. When the row is 1, here, that is column 3. You can see up here. On row 2, we're at column 6. And on row 3, you can see we're on column 9. So there is a very obvious pattern here. We can say that the column is always going to be identical to the row we're on times 3, right? And if we think a little bit deeper about where this 3 comes from, well, the 3 comes from the fact that we're moving right by 3 every time. And so we already have a formula that tells us which column to check for a tree depending on the row we're on. And since we have all these rows in our input, it's very easy to say, well, the first row we just check the row we're on times 3, that column. Now the problem comes from when we get to the end. When we get to here, once we get to row 10, we're checking 30. So when we get to row 11, we're going to be needing to check. Does that work? Yes. We need to check down 1, right 3. We need to check this spot, which would theoretically be column 33. But we can't check column 33 because we don't have it in our memory. Our representation of the slope is only goes up to 30. So how can we efficiently check this column? And that's where modular maths comes in handy. You saw me copy paste this, right? And so we know that when we get to this point, all we have to do is loop all the way back to the beginning, to here, and then start counting 3 again. This column here is the same as this column here, and what we can see is that this column here is column 2. So how do we get 2 from 33? And it just so happens that there is this concept in maths called modular maths, which solves this problem completely. And in programming, this is exposed by an operator that is usually a percentage sign, but sometimes it's also just the word mod. But in JavaScript, it is the percentage sign. And to do a really small example of what this does is if I had the numbers, let's say 0, 1, 2, 3, 4, 5. How do I do this? It's basically saying it's basically saying if I have 0 mod 3, I get 0. If I have 1 mod 3, I have 1. If I have 2 mod 3, I have 2. But once I get around to 3 mod 3, I go back to 0. 4 mod 3 is 1, 5 mod 3 is 2, and 6 mod 3 is 0 again. And so this gives me a way of bounding my numbers, even as I keep going bigger and bigger, into the range of 0 to 2, which is 1 less than 3. So there's automatically a way of looping over and over the same digits. And it just so happens that the way we can, what this means is that if in programming, this happens a lot, is if we have something, in this case, a representation of the slope that is a certain length, if we take whatever number we want and we mod it by the length of that thing we're checking, we're going to always end up with a number that is inside that list, that fits inside that what we have. And so that's what this thing here was doing. This is the parameterized version. So we'll use the non-parameterized version just to make it a bit more obvious what's happening here. When I have code like this down here, and we're just gonna shove it down here so we can see it by itself. What this is saying is we're going to loop over every value in this list. And if I use a bit more descriptive naming, you can see what's going on. Cool. Maybe we'll do it like this. So what this bit of code is saying is that we're going to loop over every row, every row of the input. So let's say we take the first one. So we have this first one. So we know the row is 0. The value of the variable row starts at 0 and it increases by 1. See, this plus equals 1 increases by 1 and every time we run this loop. We're going to get slope. Slope is going to be that particular line in the input. And column, what we do is we go row. So this is row 0. So 0 times 3 is 0. And we mod the length of this string so that we have bounded the offset within it and we can check the correct position. And so the first time we run this code, row is 0, column is going to be 0 times 3, which is 0, mod 31, which was the length. You know what? Let's just do this. That would make it very clear what's going on, because we know that the length is 31. So it will check the first column on the first iteration. And the second iteration, row is 1, so 1 times 3 is 3, mod 31 is still 3. So we end up checking 0, 1, 2, 3, this value, but of the next data. And so on until we reach the end of the array. If we go right 3 more, we end up going 1, 2, 3 onto this spot here, which you can see is column 2. If we take the row that we're on, when that happens, we were on row 11. 11 times 3 is 33, but mod 31, 33 mod 31 is 2. The other way to get mod is if you just take the remainder of the division. So 33 divided by 31 is 1 remainder 2. And so that's what mod is. The other way to think about mod is that it just gives you the remainder. But it basically loops us back around to the number 2, which is something that we can index into the array for, and it is the correct corresponding column. So that's kind of what's happening there. And I hope that was kind of like a bit of a better explanation of what's going on. Because now that I've said it, I realize I still didn't do it justice. But that's okay. It's a learning experience for all of us. And so the only other thing that happens in this code is the fact that in the second part of the question, it's asking us, well, okay, so you know how many trees you hit if you go right 3 and down 1. Now I also want you to check what happens if you go right 1 down 1, or right 5 down 1, or right 7 down 1, or right 1 down 2. And so what changing it into a function lets you do is it lets you parameterize those things. In the original code, I had this. I was it originally said I++, and I++ is equivalent to I plus equals 1. And so when we had this particular configuration, which was part 1 of the question, how did the numbers 3 and 1 end up embedded in the formulas? The 3 ended up here. Why was the 3 here? Because we went right 3 every time, right? And so in this case, all we have to do is go right either 5 times, or 3 times, or 7 times, right? If we went right every 5, then yeah, once we hit 30, the next column we want to check is column 4, which is 35 mod 31. And so this is the value here. If we parameterize this value with the number of spaces going right, it's always going to give us the right answer. And similarly, with the number of lines we go down, that's what this I is, right? I was the row that we're on. And if we have to go right 1, down 2 for the very last input, instead of going down just 1 row every time, we go down 2 rows every time. And so that's why this was I plus equals down over here, and that was I times right over there. And so hopefully that gives you a little bit of a better idea of what I did in today's challenge. Let me know if that was helpful or not. I will try to, again, this is a learning experience for me, but I will try to do my best to explain what I'm actually doing or thinking as I go through these puzzles. But yeah, hopefully that was helpful for you, and I will see you again tomorrow.